In this video, I want to cover a recent paper on securing LLM agents from prompt injection. Now, I don't usually cover individual papers on this channel, but this one earns the spotlight because it pulls together the past few years of research and practice in securing LLM agents. It's one of the most useful and well-constructed resources that I have seen on this topic. And the breadth of people that contributed to this paper is also worth noting. There are authors from many different organizations, such as lead author Luca Beurer-Kellner from Invariant Labs, together with people from IBM, EPFL, ZTH Zurich, Swisscom, Google, Microsoft, and I won't even attempt to say and likely butcher everybody's name here. But this variety reflects both the complexity of the problem and the growing consensus that to deal with it, we need to focus outside of LLMs themselves. The paper presents 6 design patterns that can be used to build secure LLM agents, specifically patterns that rely on external controls rather than trying to fix the LLM itself. And as we've seen on this channel many times, all modern LLMs suffer from inherent security issues, the worst of which is prompt injection. Just this month, I covered the echo leak vulnerability in Office 365 Copilot. That was a zero-click exploit where an email containing a prompt injection could silently exfiltrate private data from a user's account. So instead of trying to patch the models, the authors of the paper focus on a different question. What kind of LLM agentic systems can we safely build and deploy, even with those underlying LLM vulnerabilities? They walk through 6 design patterns, when each one is a good fit, what security properties it gives you, and what trade-offs it introduces in terms of functionality and flexibility. As I was going through this paper, I also ended up putting together a small repo with basic code samples for each pattern, so that I could understand them better. I'll show you the code and the demos throughout the videos, and hopefully seeing the patterns in action will make it clearer for you too. Sometimes code is just the best way to get a real feel for what these designs actually mean. First off, the paper starts by defining the problem space. What are LLM agents? How does prompt injection affect them? And what are the current defense strategies? An LLM agent is a system built around a language model that can process data and instructions and that can interact with the external environment, typically via tools such as APIs, search engine, code execution, or file system access. Agents are often implemented as conversational workflows triggered by a user prompt, but they can also be non-conversational. A typical pattern to build agents is called react, reason and act, and I have covered this on my channel in a previous video. But in a nutshell, in an agentic workflow, an LLM is used to interpret the request, plan a set of actions, and then call tools to complete the desired task. This ability to interact with the environment is what makes them useful and also what makes them risky. The main cybersecurity risk comes from the fact that LLM agents process input from many places: user prompts, documents, emails, web pages, and any of these can contain prompt injection attacks. Prompt injection is when an attacker hides malicious instructions in that input to hijack the LLM's execution flow. That lets the attacker influence parts of the model's output. Depending on what the agent can do, this might lead to things like leaking sensitive data, social engineering, exhausting system resources, or even triggering unwanted and unauthorized actions, especially if tool use isn't tightly controlled. If you want to learn more about prompt injection, I recommend you watch my DeepSec talk last November, where I break down attack types with many demos and examples. So now that we understand the problem space, the paper looks at some of the most common defense strategies adopted in the industry, and it splits them into 3 buckets: LLM level, user level, and system level. LLM level defenses focus on the model itself. This includes adversarial training, like the instruction hierarchy approach used for GPT-4o Mini to make models more resistant to prompt injection. They also include prompt engineering techniques like spotlighting, where prompts are structured to help the model distinguish trusted from untrusted content. These all contribute to reducing the attack surface, but they can be bypassed and don't offer strong guarantees. Then we have user-level defenses, which involve human-in-the-loop checks, typically asking users to confirm actions before they are executed. This can help prevent unauthorized behavior, but comes with trade-offs. It limits automation, and if confirmation is required too often, users might get fatigued or distracted and end up approving actions without reviewing them properly. Then we have system-level defenses, which fall into 2 broad categories. The first is input and output filtering, using tools like LLM-based prompt injection detectors to scan for non-malicious patterns before prompts reach the model, or to catch dangerous outputs before they are used. Examples include systems like Azure Prompt Shields and AWS Guardrails. These mechanisms are useful for reducing the attack surface, but they are heuristic in nature and therefore can be bypassed. The second category of system-level defenses is isolation mechanisms. These include sandboxing tool execution, enforcing permission boundaries, and in general making sure that even if injection occurs, the consequences are tightly contained. Crucially, the 6 design patterns outlined in the paper are themselves structured implementations of these isolation concepts, as we'll see shortly. And this paper directly addresses this issue, that common prompt injection defenses remain brittle because they mostly depend on heuristics. Given that all modern language models are inherently vulnerable to prompt injection, the authors instead explore a practical question. What kind of agent designs and structural patterns can we use today to build secure agents, even considering these underlying vulnerabilities? They divide existing design patterns into 6 categories, analyzing each one in detail regarding their security properties, appropriate use cases, and the trade-offs between safety and functionality. Here's the core principle from the paper. Once an LLM agent ingests untrusted input, it must be constrained to prevent that input from triggering any consequential actions, that is, actions that could negatively affect the system or its environment. Practically, this means restricting agents from invoking tools that could compromise system integrity or confidentiality, and ensuring that their outputs don't create further risks, such as leaking sensitive data or influencing future agent behavior. The action selector pattern maps user instructions directly to a fixed set of predefined and safe actions. These actions and their input values are determined in advance, so the agent cannot perform arbitrary or unexpected behaviors suggested by malicious input. Moreover, no LLM-generated output is ever shown to the user. The advantage is clear. This approach blocks prompt injection from ever triggering unauthorized actions or causing malicious outputs. The trade-off is a lack of flexibility. The agent can only do exactly what developers anticipated and nothing more. So now let's jump into the repo to see this pattern in action. Here we have a customer support chatbot with a list of allowed actions like greeting the user, checking order status, canceling or requesting a refund. Now, when I say hi or hello, the LLM chooses the greet action and I get a greeting. Importantly, this is hard-coded, not LLM output. If I request a refund, the LLM just picks the appropriate refund tool without passing any arguments or inputs to the tool. Now, the refund tool then shows the user a fixed set of allowed actions within this refund workflow. That is a list of orders that are eligible for refunds. And this does not involve calling any LLM. So as said, here there is no chance of prompt injection. We also have a second variant where we do allow the LLM to pass some safe parameters to the tools it selects. And as we can see in this case, we are verifying that only an order ID that belongs to the user is accepted. So in a normal flow, all works as expected, as we can see here. The LLM passes the right order ID. But if we ask the LLM to try an order ID that doesn't belong to us, this will be rejected. The plan then execute pattern has the agent generate a complete action plan with the sequence of all tools to use before it sees any untrusted data. Once the plan is fixed, the LLM can only fill in parameters left as placeholders, such as the body of an email, but cannot change the sequence of actions or any parameter that was fixed in the plan, like, for example, the recipient email address. The primary advantage is maintaining control flow integrity, ensuring the agent's behavior cannot be influenced by an attacker. The main limitation is that the agent cannot adaptively change its plan based on new unanticipated results encountered during execution. This makes it more restrictive and limited than the common React pattern, where the LLM doesn't have to commit to a full plan in advance and can adapt the next action based on the feedback of the current action. Remember this, as it will be a major distinction between the different patterns. Alright, let's look at this in practice. Here, the agent has tools to read the user's calendar and send emails on behalf of the user. When I ask it to send today's schedule to my boss, the LLM creates a plan with two actions. First, it needs to fetch my calendar, and secondly, it needs to email that calendar to john@corp.com. Importantly, the recipient address in this plan is fixed. Only the email body is a placeholder that the LLM will fill in later after, obviously, it's read the output from the first tool call, as we can see here now. So, if a meeting invite in my calendar has a prompt injection in it, let me just enable it now, it might be able to corrupt the body of the email sent to my boss, but the action plan and fixed parameters cannot be changed. So here we see that the orchestrator stops this email from being sent because the recipient address doesn't match what's in the plan. LLM Map-Reduce handles each piece of third-party data in isolation, using a separate LLM call for each one. This means that a prompt injection attack in one input cannot affect others. Each LLM call is asked to process individual inputs and extract specific fields into, say, a JSON object, and strict schema validation ensures only valid expected data passes through. Once all data is mapped and validated, a separate reduce step aggregates the results, never seeing the original potentially malicious input. The reduce step could be an LLM call itself, but could also be implemented just in code for simple cases where an algorithm can perform the required tasks by processing the returned JSON objects. The cost is some added complexity in orchestration. For example, in this demo, we have a chatbot that processes a batch of CVs or resumes. In the map phase, multiple LLM calls are used to extract structured fields from each individual CV, like programming languages and work history, and this essentially maps the CVs to individual JSON objects with very specific properties. Now, if one CV has prompt injection in it that causes unexpected or unwanted output, obviously the JSON schema validation will fail and the CV will be discarded. Now, the reducer step then can answer the user question using only valid, clean, validated JSON objects, and prompt injection never gets past the map step. The fourth pattern described is called dual LLM and is a generalization of the previous Map-Reduce pattern. It was originally proposed by Simon Willison, and it involves two LLM types: a privileged LLM that has tool access but never directly sees untrusted input, and a quarantined LLM that handles untrusted data but has no tool access. The two LLMs typically communicate via symbolic variables. This ensures that even if the quarantined LLM is compromised by a prompt injection present in some of the untrusted input, it cannot trigger privileged actions or access other sensitive data. This is more flexible than the previous Map-Reduce pattern, and the privileged LLM can prompt the quarantined LLM with any arbitrary task. The main trade-off here is added orchestration complexity. Finally, this still leaves some corner cases where the output of the quarantined LLM could still lead to some security issues. So let's walk through this demo where the chatbot has access to various emails. As we can see here, the quarantined LLM is just a tool that the privileged LLM can invoke with an arbitrary prompt to process a single email. This is important, just one email. Suppose I want to summarize all of my emails. Then the privileged LLM uses a tool to fetch the list of emails. Then, for each of them, it instructs the quarantined LLM to generate a summary, which is stored under symbolic variables. The privileged LLM only refers to these variables. It never handles the summaries directly. Now, when all summaries are collected, a safe non-LLM based function can combine them together to print the answer back to the user. This means that no injection payload in one email can ever cause the LLM to see or access information from other emails for malicious purposes. But the key point here versus the Map-Reduce approach is the flexibility. You see, here I can ask anything about my emails, and the privileged LLM can dispatch the quarantined LLM with any target prompt to complete the specific task that I'm asking for. For example, I can ask if any of my emails are asking for meetings. As we can see here, the privileged LLM decides to dispatch the quarantined LLM on each email asking to look for meetings and to return either a summary of the meeting or none if no meetings are present. All these outputs are then stored in variables which get passed to the collate function to produce a safe answer. The code then execute pattern takes plan then execute a step further. Instead of just planning a sequence of actions, the agent here can generate an entire program, say a Python script, before seeing any untrusted input. Only after the code is finalized does the agent pass in input data. This approach is more versatile than plan then execute, because the generated code can include loops, branching, and in general more complex logic, making it possible to handle more complex operations. Not quite as flexible as React, where the LLM can decide its next action based on seeing the complete output of the previous tool, but good enough for many tasks where branching and the different options are predictable. A further extension to this pattern is called Camel and was presented by Google in a recent paper. Here, they essentially add fine-grained security to the code then execute pattern by attaching explicit policies to each tool and data flows. Before any action runs, like sending an email or writing to a file, the interpreter checks that every value and operation complies with the assigned policy. This way, we can tightly control how sensitive data moves through the system and which actions are ever permitted, even when handling untrusted inputs. The trade-off is that we need a sophisticated interpreter to enforce all these checks, and error handling becomes trickier, since input data can still cause failures, but the attack surface for prompt injection is drastically reduced. Alright, let's start by seeing the basic version of this. Again, here we have our tools to manage a user's calendar and their mailbox, and we also have a quarantined LLM from the dual LLM pattern we saw before. Now, I can ask for a task like, fetch my calendar and email the summary to my boss. The LLM first writes a script that calls the required tools in sequence. When executed, even if the data contains a prompt injection, it can't alter the control flow. The email parameter cannot be modified. However, here, because one of the tools is an LLM, the quarantined LLM, there could still be an issue. What happens, for example, if the script generated by the LLM combines together a calendar invite from one user with an email from a different user and passes this combination to a single call of the quarantined LLM? Well, in this case, a prompt injection in the email could have access to the data in the calendar invite and could perhaps exfiltrate this data via, let's say, a markdown image. So to solve this, we can do something similar to what Google proposes in their Camel paper. We can essentially keep track of data flows and create a policy that states that the input strings to the quarantined LLM can only come from a single source, while the print method, which doesn't use an LLM, can be used to handle strings from multiple sources. So, if the code tries to mix strings from different sources and pass the results to the print method, all works fine, as we can see here. But if the LLM tries to pass a string which is concatenated from different sources to the quarantined LLM, the policy enforcement kicks in and the call is blocked. Finally, we have the context minimization pattern. Here, we extract a structured representation of the user's intent, such as a set of parameters, and then discard the original prompt before processing any actions or generating any responses. This prevents hidden instructions in the prompt from influencing tool usage or the final output. But it also means that the agent can't use subtle context in the prompt or prior phrasing from the input to inform its response. So to illustrate the context minimization pattern, here we're going to use this medical leaflet chatbot. When I ask a question about the medicine, the LLM is only allowed to output the list of sections in the leaflet that might be relevant to answer the question. The original question is then discarded and never used. So then a second LLM call is used to generate a summary using only the content of those sections that were selected by the first LLM call. Now, since the response generator, this last LLM call, never sees the input prompt, any potential jailbreak or prompt injection has no effect on the final output. The paper also includes a series of case studies that examine which design patterns apply to specific real-world agents and what the practical security and usability trade-offs look like in each case. The analysis highlights how different use cases, such as a file system assistant or a SQL query builder or a customer support bot, place different demands on security and functionality. For example, agents dealing with highly sensitive data or powerful tools require more restrictive patterns to reduce risk, even if that limits flexibility. Beyond the 6 patterns, the paper also outlines additional controls that apply across the board, things every LLM agent or application should really be doing, no matter what its design pattern is. These aren't architectural strategies like the 6 we covered before, they are defense in-depth controls that reduce the overall attack surface. Let's take a look at them. One is sandboxing, executing actions like code runs, file access, or tool usage in tightly constrained environments. This ensures that even if something goes wrong, the blast radius is minimal. For example, we run code in containers with read-only file system access and minimal permissions. Then there is structured output enforcement. Agents should be constrained to produce outputs in a predictable and verifiable format, such as JSON objects with specific fields and whitelisted values. This limits the space of operation of attackers and what type of content they can push into downstream systems. And yes, that includes avoiding free-form HTML or Markdown when safety matters. Then we have permission boundaries, which are also essential. Agents should never be allowed to perform actions beyond the permissions of the user they're working for. Just like in classic system security, we apply the principle of least privilege. Then there's user confirmation, which is a useful safety net. That is, having the user review and approve high-stake actions before they're executed. The catch here is that too many of these checks can lead to fatigue. If you nag the user every time, they stop paying attention. So it has to be done carefully. Batch confirmation, summarized clearly to reduce friction. Finally, there's data attribution. Agents should expose what inputs and what sources contributed to their outputs and decisions. This builds trust, helps with debugging, and gives users visibility into what's going on. That said, robust attribution is still a hard problem, especially when multiple inputs are bundled together during reasoning. I also wanted to quickly add a couple of operational controls I always recommend to my clients. The first is enforcing strict per-user rate limits, not just overall system throttling, but making sure that each individual user can only submit a certain number of requests in a given window. This is critical for two reasons. It stops a single user from exhausting all resources, and just as importantly, it slows down their ability to experiment and discover effective jailbreaks or prompt injection attacks against your system. Alongside rate limiting, I usually suggest content moderation lockouts. This is similar to account lockout after too many failed password attempts. If a user repeatedly triggers guardrails or content moderation events, their account should be automatically suspended for a period of time. That strongly discourages users from actively probing and tampering with your system. These controls don't prevent prompt injection by themselves, but when used along one of the 6 design patterns that we looked at, they do reinforce the security boundaries and considerably reduce the attack surface. From a practical engineering perspective, there are some important considerations when implementing these patterns. First, performance overhead is something you'll need to think about. Patterns like dual LLM or Map-Reduce require multiple calls to different LLMs that can quickly add up in terms of latency and cost. Then there's orchestration complexity. As you add more isolation boundaries or symbolic communication layers, the logic to coordinate them becomes more involved. You likely need a dedicated orchestration layer to manage planning, delegation, and result handling across all of these sub-agents. To sum up, prompt injection remains a fundamental risk for LLM agents, and most existing defenses are brittle and based on heuristics. The approach in this paper is to focus on how we structure agents, choosing patterns that provide strong architectural constraints instead of relying on LLMs for security. We walked through 6 design patterns, each with its own security properties and trade-offs, plus examples and practical considerations from real-world cases. We also covered cross-cutting controls that should really be implemented in any LLM application. The main conclusion is that robust security for LLM agents comes from these engineering patterns, not from clever prompt engineering or heuristic detection. General-purpose agents still come with significant risk, but by focusing on domain-specific tasks and picking the right design for our threat model, we can build useful and secure systems even today. As usual, you are on YouTube, so if you enjoyed this video, play the game, that is, click the like button, drop a comment below, and subscribe to support the channel.